All right, and at first we are born, we get held in our parents' arms, and then we begin to move around on the ground a little bit. Maybe we're not quite crawling yet. We're kind of moving around on the ground. And that's what I like to think about the area of a rectangle formula. Because this is a theorem. This is a proven theorem here based on our square postulate that we had just a second ago. Remember, area of a square is one side length square it on up, postulate. Okay, so that's your being born, you're being cradled around. That's all you know so far, how to get the area of a square. Now you're kind of walking around, trying to move on the ground a little bit here. Maybe you're not sitting down, sitting straight up. That's kind of one of the first things you do as a child. So this is a pretty easy formula. You should all know this by now here, to be honest. Area of a rectangle is base times by height. Okay, so those are dimensions of the particular shape. And height, as I explained it last class, when we see h here, first of all, b and h are both lowercase, okay? Both lowercase here. A is a two-dimensional calculation, right? It's a result, it's a product, okay? So when we have products, typically they're uppercase here. It's saying this area is composed of something, okay? B and h, they're lowercase because they're dimensions, right? They're dimensions of something. There's the base dimension, okay? We'll call this the base of a rectangle, and then we'll call this the height. And I'm doing it in such a way where, we can't use the grid to bail us out because that's, I don't know, 1.3 or something like that. We can't see perfectly, but that's it here, okay? And then height is over here. Want to remind you, though, that height, as it stands for in these formulas that we're going to deal with, should stand for altitude. Okay, should stand for altitude. The altitude, we've already studied that in triangles for sure. The altitude is the distance from a point, a vertex on a triangle to the line containing the side opposite. Okay, an altitude of a quadrilateral, or specifically a parallelogram here, an altitude would be any distance between opposite sides. Okay, so I can get the h here if I wanted to. I can get my h in the middle of the rectangle, okay? Because ultimately rectangle is a parallelogram here, and we know that any point on one of two parallel lines is equidistant from that other parallel line here, okay? So I get my h that way, I get my h this way, and I can get my h over here, of course. I can get my h on this side, okay? So if it's a rectangle, rectangles are, of course, the sides are perpendicular to each other, okay? So the consecutive sides are perpendicular, so this would indeed be classified as an altitude of that parallelogram here, of that rectangle. We get the side for free, okay? So if we know the dimensions, meaning the side dimensions, we can get the area of a rectangle, and we can simply use this formula, okay? So you might be wondering, where did this come from? The proof of this is in the book. I think it's pretty interesting. There it is right there. It's going to involve the square postulate, the square postulate. So what do you think they built out of this kind of generic rectangle they have up here? Look at this, base times height. We're trying to prove that that's area. Area equals the product of this base length and times its height dimension, so the two dimensions that we have there. They built a square, okay, which is exactly what we're going to do now, so that you get an idea of, well, I had a equals s squared for squares. How can I get to a equals the base length times by a height length for rectangles? So it's going to require the square postulate. It's also going to require something called the area addition postulate, which I'm kind of skipping over this here for sure because, I didn't need to watch a lecture on this. You don't. Thank you for watching, though. Area addition postulate is that we can add two different areas, right? So if I have another rectangle over here, for instance, and I knew the area, I could add these two areas together and it would give me the area of the whole shape here. So that's area addition postulate, very similar to arc addition postulate, similar to angle addition postulate, similar to segment addition postulate, part plus part equals whole, okay? And then there's also something called the area congruence postulate as well, which I'm kind of skipping over this here. Anyways, I think all we need is the area addition postulate for this one, okay? So the key to actually proving this, that here, I want to prove it, and I want to prove that with my green. I'm going to do this in green right now, is I can take this rectangle. This is a generic rectangle that I drew. I want to prove, right? I want to prove that A equals B times by H for this particular rectangle. So what can I do? I can build a square. Check it out here. I'm going to build a square. Well, I'm going to introduce squares that are going to get us to another square here. I'm going to put in a square down here. And I did 4, so I'm gonna try to make it visually, I'm gonna try to make it appealing to us about trying to get a square in here. So I'm gonna introduce this right here, which is going to be what? What am I introducing right here? I put a B here. I duplicate this. Ruler postulate is I can take whatever that base length is here, and I can measure it down, and I can do that at a perpendicular, right? Because through a point outside of a line, there's exactly one perpendicular I can draw. So I have drawn a B times by B squared down here, or what is it? It's B squared. Okay, B squared down here. Okay, so if you've done algebra 1 and you've done really much math at all, you're used to this sort of model of that side times by side, a side squared gives me the area of a square. So anyways, now you're doing geometry. It's just an assumption in geometry here. Okay, so this part here is B squared here. I'm going to keep making a square. I'm going to keep doing it here. Okay, I'm going to keep making a square. It's not going to happen quite yet, but I'm going to do that by introducing another square, and I'm applying the square postulate that I talked about in video number 1. So what am I going to do? I'm going to actually take this. This is H right here, right? This is length H because this is a freaking rectangle after all. And I'm going to take this, use the ruler postulate, measure out this distance here, and I'm going to extend this line as large as that H is here, okay? So then I got H over here. And I can do that, right? Any line segment has a particular measurement to it, particular length, and the ruler postulate says that's a real number that we have. So we can duplicate that over here, okay? And if I duplicate that over here, and I draw at the perpendicular over here, right, through outside a point, exactly, outside of a line, a point outside of a line, exactly one perpendicular can be drawn, and I'm having trouble drawing that perpendicular in here. There we go. Okay, so it's drawn in such a way it's perpendicular, but this again would be side H here. So here I'm just basically introducing a square. I'm introducing this. Oop. Doesn't really look like here. I don't think I can do it super straight here. It's gonna auto-correct me. So let's go with that. Okay, I think that's pretty good. And here, what do I have right here? Let me switch colors. I have built an H squared, right? An area of H squared square, because this has all the side dimensions of the height of this rectangle right here. Okay, where am I going with this? Where am I going with this? Well, I'm going with this with an area model, similar to algebra 1. Area on the outside of a square multiplying together equals the area on the inside of the square. So bear with me for a second longer here, because I am going to complete my square right now that's going to get me to finishing this proof, this very neat proof. Which again, you don't have to watch this, you don't have to know this one perfectly, but I think it's a pretty neat proof of where the heck this area equals base times height came from, like why we know this has to be true other than through observation. Well, check it out down here. What is this down here? What do you notice about this rectangle? So it's no longer a square. No longer a square down here, because that wasn't a square originally, wasn't it? Well, this is side length H. What's this side length? It's B. Okay? So here we have the original rectangle that we're trying to prove here. Its area, okay? It's trying to prove here that its area is B times by H, okay? B times by H. Is this area B times by H? Is this area B times by H? Well, no, we're trying to prove it. We're trying to prove it. We don't know yet. B times by H would be B times by H, right? We know eventually that this area is going to have to be B times H, but we haven't proven it yet. So the question is, how can we prove this, okay? It turns out this is going to rely perhaps a bit on something you've studied in Algebra 1. I know I spent a lot of time teaching it this year, but let me get rid of the B times H, okay? Going to rely on something called the area model, where you can write the area of an expression, right? A rectangle that you have here. You can write it as a sum, okay? Area as a sum, okay, equals area. Do you guys remember this all from Algebra 1? If not, not a huge deal, but I try to emphasize because I think it's very good to kind of know here that the area of a sum equals the area as a product, okay? Area as a sum equals area as a product, okay? And that's true for any rectangles, right? Which eventually another one you used to assume is true for rectangles, but it is true for any rectangles. It's true certainly for a square, right? For a square, because the area addition postulate tells me, area addition postulate, which I skipped over in the book, it tells me that if I add these 4 components up here, that's my area as a sum, okay? If I add this shape, this shape, this shape, this shape, these 4 shapes make up this perfect square over here, okay? Right here, right here, right here, and right here, okay? So I can add up 1, 2, 3, 4, and that would be one way to get the area of this whole square. But there's another way that we have to calculate areas of squares now. Why? Well, it was an assumption. It was the postulate. We have the square postulate here. So I can also write it as a product. My area is a product, meaning I can multiply base, which isn't b. It's not b for this big square. It's what? B plus h. Okay, b plus h. So my area as a product is my side here is b plus h. My height here is b plus h. I got right angles everywhere. What is this? It's a square, okay? How do I get the area of the square? Well, it's the length of one side and then square it, okay? So you can do b plus h squared. That's how I can express what I built here in terms of a square. Stay with me. What are we trying to find, though, ultimately, okay? What I'm trying to prove right now, why am I going on so long about this? And this is why I'm skipping over the class this year. I'm trying to prove this, right? This is what we originally had. And then we built a square out of it here. Because I'm trying to prove that this equals b times by h. Well, here I have b, here I have h. I'm going to get back to that soon. So what I'm going to do right now, and you can read this in the book. This is basically just taken straight from the book. And I just want to walk you through the proof if you decide to read it and want to spend a little more time with it and kind of hopefully get it a little bit better. It's my objective here. I'm going to assign this a variable, okay? I'm going to say let the area of the rectangle, right, the one of interest we're trying to find, equal h. Sorry, not equal h, equal x. Okay, equal x. So I'm going to give it a variable, I'm going to assign it a variable. And then I'm going to hope to prove at the end of this, because I'm going to have to simplify this equation soon, I'm going to have to try to prove that x equals what? B times by h. If I do that, then I found that the area of the rectangle would equal b times h. So anyways, I'm going to make this x right here because I have two congruent rectangles right here. By adding that perfect square, that b squared there, adding that h squared there, I have another space for this b, base length of b and height of h rectangle over here. So I have x here, I have x here. So my area as a sum, okay, area as a sum of this square, okay, using the area addition postulate, which I know I kind of skipped over this year. Okay, it is what? It's b squared plus h squared. Okay, it's all the component pieces. B squared plus h squared plus 2x, right? We have two of those rectangles right there. Let's solve for x, shall we, in terms of b and in terms of h. Look, we have bh there, we have b and h there. Ooh, nice, because we want to get x equal to b times h, because then we would have proven it, that the area of a rectangle equals base times by height. Okay, so I'm going to do that here, and maybe I'll just do that in one color, because the colors are getting kind of out of control right now. So here, there's nothing to simplify on this side, but what do I have here? Oh, I have a binomial square. Okay, I have a binomial square. So what do you got to remember about that? Well, you got to remember FOIL, perhaps, from Algebra 1. Okay, b plus h squared, well, that just equals b plus h times by b plus h, okay? So this is a little messy. Maybe I'll get rid of the b plus h squared and just write b plus h times by b plus h. But here, it's not as simple as distributing that 2 exponent right here. You got to FOIL, right? FOIL something called first terms, b times by b, right? The b is going to distribute to both of them, right? B distributes to the b, distributes to the h. H distributes to the b, h distributes to the h as well here. So we got to multiply 4 times. FOIL is how a lot of teachers teach it. Okay, I usually teach it usually with a generic rectangle. Okay, but I'm not going to do that now. We got enough rectangles in this problem here as it is. This proof here it is. So anyways, b times by b is what? B squared. Okay, that's my first terms together. B times by b. FOIL, right? We're going to multiply 4 times. Outer terms, b, and then h are the outer of the 2 binomials. So b times by h is what? BH. That's nice. We want a BH there because we want to prove that x equals BH. Okay, next up, what do we have? Inner terms, FOIL, right? FOIL, F-O-I-L. Inner terms, we have h times by b. Well, that's also b, same thing as b times by h. H times by b is the same thing as h as b times by h by the associative, the commutative property of multiplication. And finally, h times by h is what? H squared. Okay, h squared. So I have this. This is another way to rewrite this from the square postulate. B plus h times b plus h is just equal to, once we multiply it, b plus h squared, it's equivalent to b squared plus bh plus h squared. Okay? And it's also areas of product is the same as areas of sum of this square, of the component parts of the square. So that is equal to b squared plus h squared plus 2x. Okay? So now I have equation. And what do I notice on both of these sides? Well, I notice that I have some terms I can pull off of that, right? Because I can subtract equal values on the same side of an equation, right? I can use the subtraction property of equality. So I can subtract b squared from this side, as long as I subtract it from that side. So I can pull both away. I can simplify this. I'm going to solve for x. You're going to see in a second, okay? I can subtract h squared from this side as long as I subtract it from that side. What do we have left? We have 2x equaling b times by h. What am I doing last? Oh, wait, no, sorry. 2x equaling, well, I'm going to combine like terms right here. 2bh, I have 2 bh's. I have bh plus another bh. Well, how many bh's do I have total? I have 2 bh's here. So 2x equals 2bh. Division property of equality, what does x equal? Well, it equals bh. And there it is. We've proven it because x was the area of the rectangle. So then a equals b times by h for any rectangle. We can prove that with any rectangle we've drawn. We can create it into a square. We can add the component parts of the square together, assign the rectangles x, okay, and then get the areas of product using the square postulate. So this is all valid based on geometric proving principles like we've done all year. There it is right there. You have your area rectangle formula. Anyways, I'll be impressed if people watch this. Thank you guys for watching. Stay tuned for the next video. We'll talk about parallelograms, where that formula comes from. Hooray.